Welcome to the video summary series for Padisco's Introductory Statistics textbook. In addition to chapter summary videos such as this one, Introductory Statistics also offers podcasts, virtual tutor e-learning, homework activities with anti-cheat and auto-grade functionality, and detailed instructor resources. Find out more at padisco.com/introstats. For now, over to the author.
Hi again, I'm Sean Thompson and welcome to the next summary in the Padisco Introductory Statistics video series. In this one, we're going to be talking about hypothesis testing. In particular, we'll be going over the philosophy of hypothesis testing, the methodology of hypothesis testing, and considerations in hypothesis testing. We'll start with the philosophy of testing. We previously covered estimation, which is one of the major fields in statistical inference, and testing is the other major field. In fact, we can explain testing by comparing it to estimation. In estimation, when we don't know anything about a population parameter, like a population proportion, we collect a sample and calculate a sample statistic, like a sample proportion. We then use the sample statistic to estimate a range of values for the parameter. In testing, it's a bit different. Before a sample is collected, someone makes a claim about the parameter, and then the sample is used to test the claim. For example, someone studying gender in sports might claim that of all fans attending national basketball games, the proportion that are female is 30%. This becomes the hypothesis for the test and is known as the null hypothesis and is written like this. When we test this claim, this null hypothesis, we create an alternative hypothesis. Now, the alternative hypothesis can be two-sided, which means that it just says that the proportion is unequal to 30%, or it can be one-sided, which means that it specifically says which side of 30% the true proportion is. For example, a one-sided test might propose in the alternative hypothesis that the proportion of fans that are female is less than 30%. Either way, in the end, we'll either reject the null hypothesis or we won't. So at the end of a test, we'll always do one of two things. Either there's enough evidence to reject the null hypothesis and accept the alternative, or there's not enough evidence to reject the null hypothesis. We can say we retain the null hypothesis in that case. So those are the major concepts behind a hypothesis test. Now let's look at the methodology of a hypothesis test. We'll get to a step-by-step guide soon, but to build up to that, let's look at the reasoning behind the method. One of the key steps in a test is to assume that the null hypothesis is true. Let's keep looking at the basketball example. Let's say we're running a two-sided test now. So we assume that the null hypothesis is true. That is, we assume that the proportion, pi, of fans that are female is 30%. And this tells us what to expect when we collect a sample. And sampling distributions allow us to be fairly precise about this. For example, let's say a sample of 100 basketball fans is going to be studied. We know that the sampling distribution of the proportion is approximately normal with mean pi and standard deviation given here. But because we're assuming that the null hypothesis is true, we know all those numbers. In fact, the mean is 0.3 and the standard deviation is 0.046. And because the normal distribution acts so nicely, we can say things like 95% of all sample proportions will fall between 20.98% and 39.02%. So if we collect a sample and it isn't in that range, we'll reject the assumption. That is, we'll reject the null hypothesis. On the other hand, if the sample proportion is in that range, we won't reject the null hypothesis. So that is where the method for testing comes from. We assume the null hypothesis value for the parameter is true. We let this tell us what to expect from a sample, and then we collect a sample and see if we get what we expect. To be more precise about the method though, we have to relate the sampling distribution to the standard normal distribution, Z. Here's a step-by-step guide for a hypothesis test. First, we state the null and alternative hypotheses. In the basketball study, these were the hypotheses. Next, we assume that the null hypothesis is true. So we assume that the proportion of fans that are female is 30%. Next, we choose a level of significance for the test. This is a value between 0 and 1 and is denoted by alpha. Alpha is a measure of how much evidence you want before you agree to reject the null hypothesis. The lower the alpha, the more evidence you need. Some common levels of significance are 0.1, 0.05 and 0.01. Let's say in the basketball example we choose 0.1. Next, we determine the critical values. These are z-scores determined by the level of significance. They're like boundary points for your test. For a level of significance alpha, the two critical values are z sub alpha on 2 and minus z sub alpha on 2. These values are such that as a proportion, alpha of the standard normal distribution lies outside the critical values. For alpha equal to 0.1, the critical values are plus and minus 1.645. Next, we determine the region of rejection. This is the region of z outside the critical values. And this region is very important for how you conclude the test, which we'll explain in just a minute. But first, the next step, you collect a sample. You do this to calculate the sample statistic, which is what gets compared to the null hypothesis. So let's say you collect a sample of 100 basketball fans and that 35 of them are female. This gives a sample proportion of 0.35. Next, you calculate the test statistic. The test statistic is a very important number in your test. It'll determine whether or not you have enough evidence to reject the null hypothesis. Put simply, the test statistic is a score that measures how far your sample statistic is from the null hypothesis. To be more precise, it's a z-score for your sample statistic using the transformation formula. For a sample proportion of 0.35, the test statistic is 1.09. Finally, you draw a conclusion. If the test statistic is in the region of rejection, you reject the null hypothesis. Otherwise, you do not reject the null hypothesis. In the basketball study, the test statistic was 1.09, and that's between the two critical values, so we don't reject the null hypothesis. Now, this talk is just a summary, so there are a lot of details I haven't gone into here. The main details are, as with estimation, if you're testing the mean and you do not know the population standard deviation, you have to use t-distributions instead of z. Secondly, if you're running a one-sided test, unlike the two-sided test we just saw, you only have one critical value. And finally, there is an alternative to the approach I've just been talking about, known as the p-value method to hypothesis testing. But the chapter on hypothesis testing in the PDISCO textbook gives a comprehensive look at all of these topics. To finish this summary, I'll talk a bit about the considerations that a statistician can have when conducting a hypothesis test. We were just looking at a step-by-step guide, and that will tell you how to run a test, but there are some decisions in that guide, and statisticians need to know how to make those decisions. A big example is the level of significance, alpha. What value should you choose? Well, one thing that will affect your decision is that alpha is actually the probability of committing a kind of error in the test. In particular, it's the probability of rejecting the null hypothesis when it's true and shouldn't be rejected. This is known as a type 1 error. So why not make alpha as small as possible? Well, because there is actually another kind of error, a type 2 error. This is the error of not rejecting the null hypothesis when it's false and should be rejected. And the lower you make alpha, unfortunately, the more likely this type 2 error becomes. The probability of committing a type 2 error is denoted beta. And alpha and beta are inversely proportional at a fixed sample size. So the less likely you are to commit one kind of error, the more likely you are to commit the other. You'll get more familiar with the two types of errors as you get practice seeing them in tests. So let's try a question from the PDISCO workbook. In this question, April has a number generator that produces numbers from the normal distribution with mean 10 and standard deviation 2. Augustus, who doesn't know the mean is 10, decides to test whether the mean of April's program is 15. So his null hypothesis is that the mean is 15. Augustus retains this incorrect null hypothesis, and you're being asked what type of error or errors he has committed. He's failed to reject the null hypothesis that is false, so this is a type 2 error, so we'll submit that. And we see we get personalised feedback and an explanation of the question. Not surprisingly, both kinds of errors are undesirable. Put simply, a type 1 error means that you've concluded that someone has made a false claim when they haven't. A type 2 error means that someone has made a false claim, but you've failed to unveil that. Fortunately, you can decrease the likelihood of both kinds of errors by increasing the size of your sample. But as always, bigger samples come at bigger costs in time, money and resources. So you can create powerful tests with big samples, but only if you're prepared to pay for them. So that was hypothesis testing. The key topics were the philosophy of hypothesis testing, the methodology of hypothesis testing, and considerations in hypothesis testing.